In the screencast, we have this guy pushing this rock up this hill for the gazillionth time. And it has this inclination here of 60 degrees. Notice how I'm underlining the key terms here, and the mass is given in scientific notation with a 1.00 times 10 to the 2 kilograms. That's 100 kilograms. So this guy is pushing this rock up this hill for the gazillionth time on this angle of 60 degrees, indicating the angle here of 60. That's this angle theta. And the horizontal is this direction here. So he's giving a pushing force that's parallel to the hill, so he's pushing it up this hill. And we know the coefficient of friction, that's that mu, is given as this 0.200. And we know the pushing force, that's this FP, that's 9.5 times 10 to the 2 newtons. What we're trying to do is calculate the total work done. So what we need to get first then is we first draw out this image, and then I drew in this free body diagram. Noting here that I have 1, 2, 3, 4 different forces. With 4 different forces, we're going to have to get the work for each force. So this total work is going to be the work done by gravity plus the work done by friction plus the work done by the push plus the work done by the normal force. Noting here that this is the direction that this rock is going to be moving up this hill. So in order to get the work done by each, we're going to first take the work done here by this push. The push is going in the same direction as the distance here, so the work, which is going to equal to the force times its distance times the cosine of the angle between the two. So the angle between the two, if the push is going in the same direction, then it's just going to be force times the distance, where the force of the push is that 9.5 times 10 to the 2 newtons, and the distance that we're moving is this 5.00 times 10 to the 2 meters. Newton times a meter gives us joule, and so we get this value to be a 4.75 times 10 to the 5 joules. So this is the work done by the push. To get the work done by, let's go with gravity. I saw a lot of us, we said that gravity did 0 work. So let's get this work here. We know the force due to gravity, that's m times g. So it's going to be the force due to gravity multiplied by the distance, multiplied by the cosine of the angle between the two. So we know the force of gravity, that's mg, and it's going to be times the same distance times this cosine of theta. So we know m, we know g, we know the distance, so we have to get this angle theta, where this force of gravity is going straight down, and the distance that it's moving are separated by a 90-degree angle and that angle theta. So if we have 90 plus that angle theta, that's going to be 90 plus 60. So we're going to have an angle of 150 degrees. So we know the value for the mass. That's at 1.0 times 10 to the 2, which is 100 kilograms. I'm going to multiply by g. I'm going to use 9.8. 9.8 newtons per kilogram. I could also use meters per second squared. And the distance that we were moving was that 5 times 10 to the 2, which is 500 meters. So 100 times this 9.8 times now this cosine of 150 degrees. We get the work done by gravity here to be a negative 4.24 times 10 to the 5th joules. Noting here that, notice the distance is going up this way, and there's a component of this gravity here. So this mg in the x is going in the opposite way. So that's why we're getting this negative work by gravity. So we can get the work done by the normal force. So the work done by the normal force is going to be the normal force times the distance times the cosine of 0 or 90 degrees. 90 degrees because it's 90 degrees with respect to the direction it's going. So the work done by the normal force is going to be 0 joules. And then lastly, for this work done by the kinetic friction, so this is going to be this force due to friction. We're going to be doing with the kinetic times the distance times the cosine of the angle theta. Force due to friction is mu times the normal force, which is going to be mu mg times the cosine of 60. Cosine of 60, because that's this, that's the adjacent component right here. If I have the normal force is going to be equal to the mg and the y. And if this is theta and this is the adjacent, I want to use that cosine for this mg in the y component to get that normal force. So it's mu mg cosine of 60, and then that is the normal force, so mu times the normal force. Now I'm going to multiply by that distance d times the cosine of that angle theta, and the angle theta here is going to be going from going in the direction forward for this distance to going backwards. Friction is always going to be going opposing our motion, so this angle theta here now becomes a 180. So we have the force, which is mu times the normal times this distance. So force times distance times the cosine of 180. That's going to give us, in here, a negative value from the cosine of 180. And this will give us this negative 4.9 times 10 to the 4th joules. So this is the work done by friction. So we know the work done by friction, we know the work done by the normal force, we know the work done by gravity, we know the work done by the push. Now we add them all together, and we should get around 2,000 joules.